Hi everyone. If you are watching this video, it means you are among the lucky ones to unveil the secrets of Tic Tac Toe. I'm sure you might have encountered this simple game at some point in your childhood and probably still indulge in it today. If you have heard of it, then you do know that the most common variant is the conventional 3x3 square grid that involves two players with each represented by a unique symbol. The ways to be declared a winner is simply to attain three similar symbols in a line horizontally, vertically, or diagonally.
You might be wondering, what does a simple game like Tic Tac Toe have in store to amaze you? This is where your journey of exploration begins. Let me start by asking a simple question. Do you think there is always a winner in this game? If you have played it often enough, you would have realized it is not the case. To clear any doubts you might have, we will prove it to you that there isn't always a winner in this game, which is equivalent to the notion of the draw case. For this, we shall take a look at lemma 1. Basically, this lemma employs the method of contradiction and construction of an example to prove that there exist cases whereby both players don't win, which is equivalent to the notion of a draw. To exhibit one possible case, we will demonstrate a live scenario between two players, Alvian and Amar. As you can see, neither Alvian nor Amar wins the game, and therefore they end up in a draw. So now, you can be confident of the fact that there isn't necessarily a winner in Tic Tac Toe, and you don't need to rely on plain words to convince anyone because you know it can be systematically proven. While watching the live representation, did the following question strike you at any point? Is the occurrence of a draw random? Well, you shall discover in a bit.
For now, let's explore the winning scenario of this game. I'm sure you would be curious to know, is winning Tic Tac Toe just a result of random attempts, or is there a strategy behind it? Let's examine another live representation between Alvian and Amar and see if you can deduce a particular way in which their moves are structured. So, were you able to figure out if there was a systematic method that guided Amar to victory? If you couldn't, then we shall enlighten you now with the facts you have been eagerly waiting. We will start with lemma 2, where we establish with the aid of pigeonhole principle that there is at least one cell that is responsible for at least 3 winning paths. We know that there are 9 physical cells in a 3x3 grid, and as you can see, there are 8 distinct ways of winning this game. Since each winning pathway is determined by 3 cells, this means that there are a total of 24 cells responsible for all the possible winning cases. So, with the aid of pigeonhole principle, we can determine, has shown that out of the 9 physical cells, at least one is responsible for at least 3 winning paths. With the aid of lemma 2 and some further observation, it allows us to deduce the following weight configuration for the 3x3 grid. So you might wonder what the numbers in each cell represent. Basically, it denotes each cell's degree of involvement in constructing a winning path. Let's have a look at a live demonstration. As you can see, for the cell assigned the largest weight of 4, it contributes to 4 winning paths. For the cells assigned a weight of 3, each cell contributes to 3 winning paths. Lastly, for the cells assigned the least weight of 2, each cell contributes to 2 winning paths. Therefore, this explains the weight configuration as shown. The weights assigned to each cell intuitionally denotes the priority of the cell during one's move and therefore influences the winning chances of a player. Hence, we present this as a conjecture that the best move is to stake the highest priority cell in every round to attain an eventual winning result. However, if you are quick enough, you would have determined that the priority table on its own is not sufficiently representative of the winning strategy due to the existence of 2 special cases that needs to be considered.
The first case is as shown. In this case, if player X strictly conforms to the priority table, then X will take cell number 4 as it has a higher assigned weight of 3 as compared to the other 4 available cells. However, in doing so, he will allow player O to win the game by occupying cell number 3 in the subsequent move. This concludes a precondition one must satisfy before conforming to the priority table. That is, if there is a winning path for opponent in the next turn, then occupy the last available cell that constitutes the opponent's winning path. Moving on to the second case, we can see that relying on the priority table and the first precondition from the first special case is still not completely ideal. If player X is guided by the priority table, then he has cell number 1, 3, or 5 as options since they have higher weights of 3, and if he considers the first precondition, he will decide cell number 5 to block the opponent's winning path. However, this is simply extending the game that player X can win by occupying cell number 4. So, this concludes the precondition that if there is a winning path for the player in the next turn, he should occupy the last available cell that constitutes the winning path.
Moving to the most eagerly anticipated part, we can derive a winning algorithm for this game as shown, by consolidating dilemmas, conjecture, and special cases. This provides a structure that guides a player's move. The player first determines the existence of a winning path. If there isn't, he then considers the next option, which is to determine the existence of a winning path for the opponent. If this condition is also not met, he then plans his move by conforming to the priority table. If you recall at the start, I posed a question: is the occurrence of a draw truly random? Well, the answer to this is the algorithm which can be used as a possible justification for the draw case you witnessed in the beginning. We propose that a draw case will result if both players conforms to the algorithm. To prove this, we will showcase a computer program that simulates such scenario.
This is the program that we use. It basically consists of a large outer loop which iterates through all the number of trials. In this case, it is 100,000. Every trial will run in a while loop which basically allows the players to take turns as long as the game has not reached an end. If the players does not conform to the algorithm, then they will select a random cell on their first moves respectively and move according to the algorithm on the next moves. Now, we see that if both players conform to the algorithm, the result will be 100,000 draws out of the 100,000 games played. This ascertains our hypothesis that if both players conform to the algorithm, then the game will always end in a draw. I hope it was an eye-opener for you to realize that the draw case might not be a random occurrence after all. Now, let's look at the application of the algorithm in achieving a winning case. Our proposition is, if any one player deviates from the algorithm once, the opponent conforming to the algorithm will most likely win. Once again, we will use the program to affirm this proposition.
If the second player deviates once on the first move, then this will be the result of the program. The first player will win 37,469 times out of 100,000 times, or roughly 3 out of 8 of all trials, and the remaining will be draws. This conforms to the hypothesis that a player will most likely lose if he deviates once from the algorithm. You will be excited to know that our analysis is not restricted to the conventional 3x3 tic-tac-toe, as it can be extended to another variant, which is the 3-dimensional tic-tac-toe. For those who haven't heard much of this variant, it essentially extends the tic-tac-toe to a higher dimension and hence incorporates the size of a 3 by 3 by 3 cube. The rule stays the same. Both players take turns to put their symbols and the first one to get 3 symbols in a line will win. Now we are going to present Lemma 1, in which the 3D tic-tac-toe cannot end in a draw. We try to prove this by using contradiction. First, we assume it is possible for us to end in a draw, and therefore every horizontal layer of it must end in a draw, and the game must still result in a draw. By observation, there are only two ways in which a layer will end in a draw. Of course, by neglecting symmetries and switching of X and O's. Therefore, there are two possible cases. First one is, if the bottom layer is of the first type, then the center middle can be an O or an X. We'll try both. If the center middle is an O, then the top layer must be as follows to prevent O from winning. Then, to prevent X from winning in the top layer must be like this. Therefore, the middle layer must be like this in order to prevent O from winning vertically or diagonally. In particular, notice the bottom line of top layer and bottom layer. However, this will result in X winning. Therefore, the center middle cannot be an O. If the center middle is an X, then the top layer must be as follows to prevent X from winning. Then, to prevent O from winning in the top line and in the top layer, the boards must be like this. However, by doing so, notice the three red axes will form a line, and therefore the center middle cannot be an X too. Now we noted that the center middle cannot be an X or an O. This contradicts with statement B, and thus the bottom layer cannot be your first type. However, this also happens if the bottom layer is of the second type, as we see here. So, the bottom layer cannot be first type nor second type. This contradicts with statement 4. Therefore, it's not possible to have 3 layers of draw and still ending with a draw. Therefore, the 3D tic-tac-toe cannot end in a draw. Now we are going to present Lemma 2, in which the first player can always force a win. Let's try to prove this by using the decision tree by eliminating all symmetries. First thing first, as the first player, X should always take the center, as the center has the highest priority. Now, there are 3 possible moves for O. The first one is by taking the corner, the second is by taking the edge, and the third is by taking the side. Next thing, X will take its turn, and O will always be forced to block X's winning path, as shown by the diagram. Again, X will take its turn, and this time it will be a checkmate for the O, as there are 2 paths that should be blocked at once, and that's not possible. Therefore, X or the first player can always force a win.